Hello everyone, welcome to Toppscholars, the smart learning app. Today in this lecture, we are going to start with a new series on electrostatics in which today we are going to learn about electric charges and electric fields. So, first of all, let's understand and let's see what exactly we are going to learn in this lecture. So, we are going to talk about what are exactly the electric charges. We are going to understand the ways in which the object can be charged. Then we are going to talk about some of the properties of the charges, that is additivity, conservation, and then quantization of charge. Then we will talk about what exactly is Coulomb's law and how important it is. Then we are going to talk about the unit of charge, then principle of superposition, and then continuous charge distribution, and then electric field, and then electric field lines. So all these things we are going to understand in this same lecture. So let's get into this. Let's start with our lecture. So first of all, let's understand what exactly do we mean by electrostatics. So basically, electrostatics is a branch of physics which studies the electric forces, electric fields and electric potentials produced by stationary charges. So over here in electrostatics, basically we talk about stationary charges and their effects in the surroundings, isn't it? Like what exactly is the force that they exert on other charges in the surroundings, what is the electric field produced by them in their surroundings, and what is the electric potential produced by them at different points around them. So all these things are studied in electrostatics. So this is the simple definition of electrostatics. Now let's understand what is electric charge with a simple example, as you can see over here. So here we can see we are trying to attract the pieces of paper using a comb. Initially we are not able to attract these pieces of paper with a comb, but later on when we rub the comb on our hair, then the pieces of paper are easily attracted, as we can see over here. Now why did that happen? So the main reason is when we rub the comb on our hair, then the comb gets charged. Some charge gets accumulated on this comb, and that's why when the comb is kept near the pieces of paper, then the pieces of paper are attracted towards the comb. So this is all because of the electric charge. So basically the pieces of paper themselves contain some charge in themselves, then some charge is accumulated on the comb, and this accumulated charge exerts some attractive force on the charges inside the paper, and that's why the pieces of paper are attracted. So basically we can say over here, this is nothing but the property of the matter that causes it to experience an electrostatic force when near other electrically charged objects. So this is simple definition of electric charge. Let's understand this with another example. So here we can see we are trying to stick a balloon to the wall, but we are not able to stick it initially, but when we rub it with some cloth, then we are able to stick it to the wall again because of the same reason, because when we rub it, then some charge is accumulated on the surface of the balloon, and that's why the balloon is easily stuck onto the wall, isn't it? So again, this is all because of the electric charges accumulated on the surface of the balloon. Now let us understand more about electric charges. So here we can see there is a simple object, as you can see over here. Now we want to understand what do we really mean by positively charged and negatively charged objects, isn't it? So here we can see a simple object. We can see over here it's a spherical object. Now basically every object, every material is made up of atoms, and every atom contains equal number of protons and electrons. The thing over here is protons and electrons have equal charge on themselves, isn't it? And the value is 1.6 into 10 to the power minus 19 Coulomb. The thing over here is protons are positively charged and electrons are negatively charged. Since the numbers are equal, since the charge is equal, that's why every atom is electrically neutral. And ultimately, everything around us is electrically neutral. Now, let's understand what do we mean really by positively charged object and what do we mean by negatively charged object. So, first of all, let's try to understand what do we mean by positively charged object. So, here we can see this object right now has excess positive charge. That means, let's say somehow by some procedure we removed some charge, some negative charge from this object. So, what remains over here is positive charge, isn't it? As we can see over here. So, this object, since it has excess positive charge, this object can be called as a positively charged object. You can see here there may be few negative charges left, but they can be neutralized by the other positive charges in their vicinity, but the remaining charges may cause an effect of positive charge. So, you can see over here there are few negative charges may be left, okay. So, these charges may be neutralized by other positively charged particles over there in their vicinity, but other remaining positive charges may make the object as a whole positively charged. So, this is a positively charged object which has some excess positive charge on itself. Now, let's talk about what do we mean by negatively charged object. So, over here we can see by some process maybe we have removed the positive charges out of it, or maybe by some process we have accumulated some extra charge, extra negative charge on this object. Now, because of this, the object has become negatively charged, as now this has excess negative charge. We can see few positive charges also present over here, but again these positive charges may be neutralized by other negative charges present in the vicinity, but the remaining charges may produce an effect that the object as a whole will become negatively charged. So, this is nothing but negatively charged object, something that has got excess negative charge. So, this is all about positive and negatively charged objects. Now, here is again the same example. Now, we want to talk about the different ways in which the objects can be charged. So, one of the ways in which we can charge any object is by rubbing. So, rubbing of insulators cause transfer of charge. Like we can see over here that when the comb is rubbed on the hair, then some charge is transferred, isn't it? And the charge is accumulated on the surface of the comb, isn't it? And that's why when it is brought closer to the pieces of paper, the pieces of paper are attracted towards the comb, and that's why the pieces of paper are stuck to the surface of the comb. So, this is one of the ways in which we can transfer the charges, or we can say one of the ways in which any object can be charged, isn't it? Same thing we saw with the balloon. When the balloon was rubbed, isn't it, with some cloth, then again it was charged. So, this is one of the ways. Now let's talk about what do we mean by triboelectric series. So, basically triboelectric series is a list of materials that indicates by position on the list which materials are capable of acquiring a positive or negative charge and the relative strength of those charges. So, basically lots of experiments were carried out with lots of insulating materials, and it was found out that some materials became positively charged and some materials became negatively charged with different strengths of electric charge. So, based on these experiments, a series was formulated and it was called as triboelectric series. So basically we can say over here, countless experiments in rubbing things together led to the observations that are summed up in series known as triboelectric series. Okay, so let's look at the series now. So basically the series looks like this. Here is the series. You can see a huge list actually, list of different materials starting with mica, and if you can see at the end we have PDMS. So this list actually indicates which material will become positively charged on rubbing and which material will become negatively charged on rubbing. So like for example we have mica. So when mica is rubbed with some other material, then it will become positively charged. So the thing over here to remember is, when mica may be rubbed with other material like let's say amber, maybe wood, then the mica will become positively charged, but the wood or maybe the amber will become negatively charged. So since mica is becoming positively charged, that means it is losing electrons. That's why it is becoming positive. And since amber is becoming negatively charged, that means it is gaining electrons. So this is what actually this series talks about. So here actually we have a huge list. You can see over here, you can note down these names also, okay, and from this list you can actually conclude which object will become positive and which one will become negative, isn't it? So there are two different surfaces, and when they are rubbed over one another, the one higher in the table will lose electrons and become positively charged, and the one which is lower in the table, that will gain electron and become negatively charged. So that is what this triboelectric series is all about. Now moving on, the prefix tribo over here, it means to rub. Since over here we are rubbing things, that's why it is called as tribo, because tribo means to rub. Okay. Now here is another question for you. Will all objects be charged by rubbing? Like over here we can see we are trying to rub a key on a cloth, right? And we are trying to attract the pieces of paper. But will this happen? Is this effect of rubbing applicable for metals or conductors? Is it? The answer is no. Only insulators can be charged by rubbing. Charging by rubbing doesn't happen with conductors. The main reason for this is conductors have huge number of free electrons, free charges. So whenever some charge is transferred, whenever some small vacancy of charges is created, immediately other charges from other places will come and fill that space, and therefore no accumulation will be seen, or we can say very less accumulation will be seen, and that's why this effect is not seen with conductors. Okay, so the answer to this question is no, it cannot. Okay, only insulators can be charged by rubbing. Okay, moving on, now let's talk about the another way of charging the objects. This is called as conduction. So basically conduction charges the uncharged body with the same type of charges. So over here we saw initially we had one object which was positively charged. Now when another object is kept in contact with the first charged object, then we can see some charge was transferred. So this process is simply called as conduction of charges from one place to another. So this is how another object can be charged, by bringing it in contact with the first body. So this happens only if the bodies are in contact. So what we have to do is, we have to bring a neutral body in contact with the charged body. So charged body will transfer some of the charges from it and it will go to the neutral body, and that's why the neutral body will become charged. So this is what happens. So now let's talk about the next way in which we can charge the object, and it is induction. So induction basically charges the uncharged body with the opposite type of charges. So what happens here is, as we can see, initially we have one negatively charged object, and what we have done is we have brought another neutral object in close vicinity of the negatively charged object. Now what happens is, since the object is negatively charged, what it will do is it will attract the positive charges of the other object towards itself, or we can say it will repel the negative charges away, and that's why the positive charges will be accumulated on the surface near the negatively charged body, and that's why the second body will be positively charged. Okay, in this way, here there is no contact. There is no contact between the two bodies, but still the other body will be charged up just because of the induction process. This simple process is called as induction. Okay, because the charge is induced on the surface due to this attraction. So this is induction, isn't it? Okay, so now let's talk about some of the properties of the charges. So over here, if we have, let's say, n number of charges on a body, then the total charge on a body is nothing but sum of individual charges on the given body. Just like over here we can see there were n number of charges, small charges accumulated on the body, or we can say distributed over the body. Then the total charge on the body is nothing but the sum of all the individual charges on that given body. So simply we can say total charge is equal to Q1 plus Q2 plus Q3 up to Qn. So we can say here that charges add up like normal numbers, isn't it? They are scalar in nature. Okay, there are no directions involved over here. So they do not have any direction. So they just add up like scalars. So this is one of the property of charges. Okay, additivity of charges. Now let's talk about the second property of charges, that is conservation of charge. So according to this conservation of charge, the total charge of an isolated system is always conserved. That is, the total charge remains constant. For example, we can see over here, when we rub the comb on our hair, then the hair transfers some charge on the comb. But this thing over here is, when the hair transfers some charge on the comb, then same amount of positive charge is developed on the hairs also. Same amount of negative charge is developed on the comb also. So if we look at the combined effect, then the total charge on this whole body, or we can say on this isolated system, that is conserved. That means for the system as a whole, the total charge is still conserved. That means here what has happened is only some charge from the hair has been transferred to the comb. Okay, total charge in the universe has always remained the constant. Okay, so whatever may be the process, the total charge always remains constant. So this is simply called as the conservation of charge. Over here we can see that the total charge on hair and comb before rubbing is equal to the total charge after rubbing. Total charge on here, comb and hair is one system we can consider, and total charge on both, it's still the same. Okay, moving on, now let's talk about quantization of charge, the third property associated with charges. So if the charge of an object is Q, it actually means that the total charge of all the electrons, say n electrons in that object, is Q. That means what exactly do we mean over here is that any charge that is accumulated on any surface, or let's say on any body, whatever charge is accumulated on any body, that is always in multiples of basic electronic charge, that is the charge on the electron. So over here, for example, if you have this simple ball on which some charge Q is accumulated, then this Q actually means that over here it is nothing but it is some multiple of basic electronic charge, isn't it? So that's why we can say Q is equal to n times. So basically we can say over here that every charge, anything, anywhere we see some charge accumulated, it is always some multiple of basic electronic charge, n times E only. We will never have any charge that is, let's say, half of E, let's say 2.3 times E. No, it will never happen. It will always be equal to some integral multiple of E only. Okay, it will never be half, never be quarter, or never be any other number, isn't it? It is always going to be integral multiple of basic electronic charge. It may be positive, it may be negative, but it will always be integral multiple of E only. So this is the third property. So basically there are three main properties of the charges. One is additivity of the charges, second one is conservation of charges, and third one is quantization of charges, which says that Q is always equal to n times E, where n is equal to total number of electrons in that particular object and E is the charge on one electron, isn't it? So this is quantization of charge. Now let's understand the quantization of charge with another example. Sometimes when there is some charge accumulated on some body, it may appear very much continuous. Like you may not be able to distinguish, or you may not be able to pick one charge because there may be huge number of charges accumulated on the surface, so it will appear quite continuously distributed, somewhat like this. Look at this line, but when we zoom in, actually these are small dots, or if you look at this from another angle, these are nothing but these children's, but when we look at from a very far distance, they will appear like a continuous line. So same thing happens with charges. When it is distributed over some object, then they may appear to be continuous, but when we go in deep inside the object, then we may find different charges here and there. All these electrons are distributed at different places. So we can say over here that the charges on a system may appear continuous, but they are discrete. Okay, when any physical quantity exists in discrete packets rather than in continuous amount, the quantity is said to be quantized. Thus, the charge is quantized. Since over here charge is always available in some packets, discrete packets, isn't it? And that the value of that packet is nothing but E, that is the basic electronic charge. That's why we can say that charge is quantized, isn't it? So this is quantization of charges. Now after all this, let's move to a very important concept, that is Coulomb's law. Coulomb's law, we can say over here that it is the backbone of electrostatics, because this actually gives us the magnitude and direction of force between two charged particles. Like here we can say, for example, we have a plus Q charge and a minus Q charge. They are placed at a distance r from each other. Then what will be the force between them and what will be the direction? That was found out by Coulomb. Okay, and he has given one very important equation, one very important law, which gives us magnitude as well as direction, isn't it? So let's look at this law now. So he says that the electrostatic force of attraction or repulsion between two charges is directly proportional to the product of magnitude of the two charges, that is Q1 and Q2. Let's say Q1 and Q2 are the two charges, and the force over here is inversely proportional to the square of the distance between them, isn't it? And also the force always acts along the line joining the two charges. So the force will never be in any other direction. The force will always be along the line joining the two charges, as we can see here also. It is over here, it is in the same direction as that of the line joining the two charges. So this is basically the Coulomb's law. So basically Coulomb's law states that the electrostatic force of attraction or repulsion acting between the two stationary point charges is given as F is equal to K Q1 Q2 upon R squared, where over here k is a constant whose value is 1 upon 4 pi epsilon naught, which is equal to 9 into 10 to the power 9 Newton meter squared per Coulomb squared. Okay, and epsilon naught over here is the permittivity of free space or vacuum. Okay, so this is permittivity. So this is the simple equation which gives us the force between two stationary charged particles placed at a certain distance r. Okay, so this is Coulomb's law. Now, the SI unit of charge is Coulomb and it is denoted by capital C. Okay, so let's understand how exactly we can define this Coulomb. So let's say we have got two charges, 1 Coulomb and 1 Coulomb. Both are, let's say, positive, and let us say that they are separated by exactly 1 meter, isn't it? Now, 1 Coulomb is that charge which, when placed at a distance of 1 meter apart from another charge of same magnitude in vacuum, experiences an electrostatic force of repulsion of magnitude 9 into 10 to the power 9 Newton. Okay, so this is the definition of 1 Coulomb. So we have got two charges which are both 1 Coulomb. They are placed at 1 meter. So according to the formula, if we get into the formula here, then the value of k is 9 into 10 to the power 9. Q1 is 1, Q2 is 1, R is also 1. So F will be equal to 9 into 10 to the power 9. So from here we can define what is 1 Coulomb, isn't it? So basically 1 Coulomb is that charge which, when placed at a distance of 1 meter apart from another charge of same magnitude in vacuum, it experiences an electrostatic force of repulsion of magnitude 9 into 10 to the power 9 Newton. So this is a simple definition of 1 Coulomb. Now let's move to the very important concept from electrostatics, that is principle of superposition. So basically, principle of superposition states that the total force on a given charge due to number of other charges is the vector sum of individual forces exerted on that charge due to other charges, like this one. So over here we have got total force F is equal to F01 plus F02 plus F03 and so on up to nth. This is basically nothing but the force on 0th charge, okay, due to the n number of charges. Since all the charges which are in the vicinity of 0th charge, they are going to exert some force. So the total force or the net force on that given charge is nothing but the vector sum of individual forces. So over here we can write in vector form F10 is equal to K Q0 Q1 upon R01 squared R01 cap. This R01 cap is nothing but the unit vector. So this is just a unit vector, or we can say this is the vector representation of the force. Okay. Now here we can understand this with a diagram. Here we have the Q0 charge, isn't it? And there are different charges, as we can see here. All of these charges are going to exert individual forces on the Q0 charge, isn't it? So all these forces will be added up vectorially. So there will be a vector sum of all these forces, okay, acting on Q0. So this is what principle of superposition states actually. So here is the equation which indicates what exactly principle of superposition tells us. So force on the ith particle is equal to K times summation of Qi Qn upon Rni squared into Rni cap, where Rni cap is the unit vector which indicates the resultant force, or we can say direction of the resultant force. Okay, so this is principle of superposition. Now let's talk about the continuous charge distribution. Okay, so the region in which charges are extremely closely spaced is said to have continuous distribution of charge. Okay, so if charges are very close to each other and they are very large in number, in that case we say that the charge is continuously distributed. So this is continuous distribution of charge. So there are three types of continuous charge distributions. One is linear charge distribution, which is characterized by linear charge density denoted by lambda. So basically linear charge density, or we can say linear charge distribution, is nothing but distribution of charges over the length of a conductor or maybe insulator. If the charges, or we can say if the total charge is distributed over the whole length, as we can see over here, over the whole length of a, let's say, wire or maybe some other material, okay, then such a distribution is called as linear charge distribution. And to facilitate the discussion, we introduce a concept called as linear charge density, that is lambda, and lambda is equal to dq upon dl, which is nothing but small charge upon small length. So charge per unit length, that is nothing but the density, linear charge density. Moving on, next is the surface charge distribution, which is characterized by surface charge density, isn't it? So over here what happens is the charge is distributed over the whole surface, as we can see over here, over the whole surface of a given body. In that case, we say that there is a surface charge distribution, and again over here we introduce a term called as surface charge density denoted by sigma, as we can see over here, and sigma is given by charge per unit area. Okay, so this is the simple definition of surface charge distribution. Moving on, the next type is volume charge distribution, which is again characterized by volume charge density, which is denoted by a rho, isn't it, as we can see over here. Okay, so basically when the total charge is distributed throughout the volume of a given body, then in that case we say that the charge has been distributed throughout the volume, and such a distribution is called as volume charge distribution. And again we introduce another term called as volume charge density, that is rho, and this rho is given by charge per unit volume. Here we have taken a small charge and divided by small volume. So this is the third type. So there are three types of continuous charge distributions. One is the linear charge distribution, second one is the surface charge distribution, and the third one is the volume charge distribution. So these are the three types. Moving on now, we are going to talk about what exactly is electric field. So basically electric field is the region, okay, around a charged body in which another charged body, or we can say another charged particle, experiences an electrostatic force. As we can see over here, we have a charge Q1, okay. Now this charge Q1 produces its electric field around itself, and this field is theoretically spread up to infinite distance, okay. Every charge produces its electric field around itself, and this field is spread up to infinite distance theoretically, isn't it? And when another charge comes in close vicinity of this charge, then it will experience some force. As we can see here, there is a charge Q0. When it comes in close vicinity of Q1, it is going to experience some force, maybe repulsive, maybe attractive, depending on the charge, whether it is positive or negative, okay. So basically electric field is the region around a charged body in which another charged body experiences an electrostatic force. So this is a simple definition of electric field, isn't it? So over here we can see Q1 is producing its own electric field, and there is a charge Q0 which is experiencing small force due to this Q1. Over here Q0 is actually called as a test charge. Generally test charges are very small in magnitude. very small, maybe in size also, and the thing is their value is very small such that they do not influence other charges in their vicinity. Even if they move, even if they are placed somewhere, they do not change the configuration of the whole system. Okay, so this is the test charge. Okay, then the Q1, which is actually producing the electric field, and we are studying the effects of Q1 on Q0, that charge is called as source charge. A charge which is capable of having its own electric field and which is able to influence other charges in its vicinity. It is called as a source charge. Just like we can see over here, Q1 is able to produce its own electric field and it is able to influence Q0, which is in its vicinity. So it is a source charge. So generally in electrostatics, while studying different concepts, we use two kinds of charges. One may be a source charge which produces the fields and whose effects we are studying, and we also use test charges which are generally very small. So this is nothing but the two types of charges that we generally use. Okay, now let us understand what do we mean by electric field lines. So to help us understand the mechanism of exerting forces on each other, we have introduced a concept called as electric field lines. Every charged particle has got electric field lines around themselves, or we can say these are the theoretical constructions to understand the forces or to understand the electric field around the charges. So basically there are two types of charges as we can see. One is positive, other is negative. So basically the electric field lines always originate from positive charges and they always end up in a negative charge. They always originate from positive charges and they always end up in the negative charges. Okay, now let's understand what do we really mean by these electric field lines and what do they really indicate. So basically electric field lines are the curves such that the tangent drawn at any point on these lines indicates the resultant force or the direction of the resultant force at that point on any test charge. Repeating, over here the electric field lines are the curves such that the tangent drawn at any point on these lines indicate the direction of resultant force at that point on any test charge. So this is basically the simplest definition of electric field lines. So basically if you keep a test charge anywhere on these points, at any point, then the resultant force on that test charge will be in the direction of the tangent drawn at that point to the curve, isn't it? So this is the simple definition. Now there is a very important property associated with electric field lines, and that is the electric field lines do not intersect, do not cross each other. If they do so, if they cross each other, that means at that point of intersection there will be two directions of the forces on a given charge. That means if we keep a test charge at that point where the two charges intersect, okay, then at that point the charge will be accelerating in two directions, which is practically impossible. That's why the electric field lines never intersect. Now the density of these lines depends on the magnitude of the charges. More the value of charge, more will be the density of these lines. More and more number of lines, field lines will be produced, okay, if the value of the charge is large. So this is the electric field line. Now after all this, let's see one previously asked question. Okay, so here is a simple question. Let a charge Q on a body be divided into two charged bodies. Okay, so we have a charge Q which is divided into two charged bodies and these bodies thereafter are kept at certain distance from each other. Show that the force between the bodies is maximum if Q upon Q is equal to 2. Okay. So what we have done over here is we have a charge Q, okay, which has been divided, okay, among two bodies, and we have to show that the force between the two bodies will be maximum if capital Q upon small q is equal to 2. Okay. So let's try to find out the solution. First of all, what is given? The charge on a body is Q. The body with charge Q is divided into two charged bodies, right? Let Q be the charge on one body, then the charge on the second body will be capital Q minus small q. Okay. Now, what we have to show here is the force F between the bodies is maximum if capital Q upon small q is 2, right? Now, let's look at the solution. So, basically we know that the force between two charges Q and Q minus Q is given as F is equal to K, which is a constant, Q into capital Q minus Q upon R square. This is nothing but the Coulomb's law, right? Okay. Now, K is equal to this value 9 into 10 to the power 9. Okay. So, let us say capital Q is equal to 6 Coulomb, for example, and R is equal to 1 meter. Okay. So, we have taken one simple example and this is our formula, right? Now, what we have done here is we have taken different values. Let's say small q is 1, small q is 2, 3, 4, 5. Then the remaining will be the capital Q minus Q, right? That means if small q is 1, then capital Q minus Q, that is 6 minus 1 will be 5. And in that way, we have calculated the force in all cases. Here we can see. So, there are different values. As you can see, initially 45, then 72, then 81, again 72, 45. So, we can see here it is increasing, then again it is decreasing. So, if we plot a graph, okay, of F versus Q, so the graph would be somewhat like this. This is F on y-axis and this is, you can see, Q on the x-axis. So, as the Q is increasing, isn't it? As the Q is increasing, the force is first increasing and then again it is decreasing. Okay. So, we can say here, initially it is increasing. That means what? That means the slope is positive. That means dF upon dQ, rate of change of F with respect to Q initially is positive, then afterwards it is negative, but there will be a point at the top where the slope will be 0. Initially it is positive, then it is negative, then at the middle it will be 0. That means rate of change of F with respect to Q at the point where F is maximum is going to be 0. So, that's our condition to find out the final solution. So, for the force F to be maximum, dF upon dQ is 0. Okay. So, dF upon dQ is equal to this, right? We can put the value of F here and all this is equal to 0. Okay. So, over here we can take out K and R squared, and if we take it to the other side it will become 0, and what remains is just Q into Q minus Q squared, isn't it? Since K and R are the constants. Okay. Now, over here if we differentiate this equation, what we will get is Q minus 2Q is equal to 0, and finally after we solve this we get capital Q upon small q is equal to 2, isn't it? And that means whenever capital Q upon small q is equal to 2, force will be maximum, and basically that's our solution for this problem. So, in this way we come to the end of this lecture. I hope you liked this lecture and I hope you have understood so many concepts related to electrostatics. So, this was the first video in the series of electrostatics and so many more videos to come. Thank you so much for watching.